let's talk about calorimetry. So calorimetry is basically the technique that is used to measure heat flow in a chemical reaction or in other physical processes. And the device that we use to carry out this type of measurement is known as the calorimeter. And calorimeters come in different levels of sophistications and designs. And the simplest one here, the low-tech version of a calorimeter is shown here. It consists of two styrofoam cups, a cover with two holes. One of the holes will have a thermometer pushed through it. The other one will have a stirrer pushed through it. And basically the way this works is that you have your process taking place inside here. So let's say it's an exothermic reaction that is taking place here. Then you can measure the temperature difference or change that occurs using the thermometer here, and other information based on the amount of substances and so on, specific heat, which we'll talk about shortly. We can determine the enthalpy change of the reaction that is taking place, all right? Okay, then we have one that's a bit more sophisticated, known as a bomb calorimeter, which is used to measure the enthalpy of combustion. Combustion, as you know, is basically the reaction of a substance with oxygen. And in this particular setup, it is used primarily to determine the enthalpy of combustion of organic compounds. Organic compounds contain mostly carbon and hydrogen, maybe oxygen, and maybe some other elements, but the products of the reaction would be mainly carbon dioxide and water, and also heat will be generated as well. So just to give a brief description of the setup here, here we have the steel bomb, which is basically where it's a steel encasing, where inside of it you will have your organic substance, which has two wires connected to it or inserted into the organic substance here. These are led to an external circuit. So when the switch is turned on, this starts burning. It, as I said before, it produces carbon dioxide and water and heat. The heat will be transferred to the water, and based on the mass of the water, the temperature change of the water, basically, and of course we have this to stir the water to make sure that the heat is uniformly distributed. So based on the mass of the water and the temperature change as measured by the thermometer here, we can determine the amount of heat change that takes place for the given amount of the organic substance here, which means we can ultimately determine the enthalpy of combustion for the substance here, all right? So that's basically how this works. So let's talk about some terms here in this section. Firstly, with respect to the calorimeter, it's very important that you understand the relationship between the heat that is evolved in a reaction and the heat that is absorbed by the calorimeter and its contents, right? So basically, we can write down a relationship which represents what this statement is saying. Q of the calorimeter is equal to minus Q of the reaction, all right? And that's because if the reaction generates heat, then it's absorbed by the calorimeter. Or if the reaction absorbs heat, then the heat is provided by the calorimeter, all right? So that's a very important relationship which we'll use later on in some problem-solving exercise. Now, in the calorimeter, what we measure, among other things, is the temperature change, right? So basically, if the reaction is exothermic, there'll be a positive temperature change because heat is generated by the reaction, absorbed by the calorimeter, and therefore the calorimeter will increase in temperature. And of course, the opposite is true if the reaction is endothermic. Okay, so some terms we need to be introduced to or reintroduced to, because I'm quite sure you have met some of these terms in your high school chemistry or introductory chemistry. So the first term here is the heat capacity. By definition, the heat capacity of a system is the amount of heat required to change the temperature of the system by 1 degree Celsius or 1 calorie. And let me just say that it doesn't matter if the temperature changes by 1 degree Celsius or 1 Kelvin. I think I said calorie earlier, it should be Kelvin. It doesn't make a difference if the temperature change is recorded in Celsius or Kelvin. The magnitude will be the same, all right? The change in temperature will be numerically the same if the change is registered or recorded as in the units of Celsius or Kelvin, all right? So that's the first thing. That's the first definition, the heat capacity. And there's an equation that you can use to calculate the heat capacity, and that is this equation right here. the heat capacity is equal to Q divided by the change in temperature. Q, of course, would be the heat change, and delta T would be the change in temperature. And as stated here, the units will be either in joules per degree Celsius or joules per Kelvin. Again, it doesn't make a difference if we have the Kelvin unit here or degree Celsius here. The value of Q would be the same, all right? Another definition that well, to be perfectly honest, I don't anticipate us using this much, or at all. But let me talk about it anyway. It's called the molar heat capacity, which is the heat capacity of 1 mole of a substance. Now, one that you'll be using definitely in this particular chapter is known as the specific heat, which is the heat capacity of 1 gram of a pure substance, right? So basically, the heat capacity, or I should say the specific heat, which is represented by lowercase c, would be equal to the heat capacity, which is represented by uppercase C, divided by the mass, right? And that therefore will be equal to Q divided by M times delta T. And we can rearrange this equation to get this form, which is a more common form of this relationship between the heat change, the specific heat, the mass, and the change in temperature, all right? So the heat change is equal to the specific heat times the mass in grams times the change in temperature, which, as I said before, can be expressed in either degrees Celsius or Kelvin. Okay, so those are some terms that you need to be aware of, and we'll be using this equation and this equation in some problems, such as this example right here. So this question says, calculate the heat capacity of an aluminum block that must absorb 629 joules of heat from its surroundings in order for its temperature to rise from 22 degrees Celsius to 145 degrees Celsius. Again, so, as in the case of examples that we have looked at before, you have to pay attention to how the question is worded, because the question says here that the aluminum block is absorbing 629 joules of heat, and it says here that the temperature change is from 22 degrees Celsius to 145 degrees Celsius, all right? So, let me go back to my black ink here. So, remember now, I showed you earlier that the heat capacity is equal to the heat change Q divided by the change in temperature, right? Now, because it absorbs 629 joules of heat, the heat change here will be positive. So you're just going to write 629 joules above. And then as far as the change in temperature, whenever, and I made this point before, and I'll say it again, whenever you're trying to determine the change in any quantity, it's always the final value minus the initial value. The final value minus the initial value. So therefore, the final value is 145 degrees Celsius minus the initial value, which is 22 degrees Celsius. And all we have to do is the number crunching. From here, what I would do is work out the denominator first. So 145 minus 22 equals that. And then I would divide 629 by that. So let me do this again. 145 minus 22 equals that. And then I would divide by 629. And according to my calculations, this works out to be, when rounded off to 3 sig figs, this works out to be 5.11, and the units would be joules per degree Celsius. And that's basically how that is done. All right? Okay, so much for that example. Let's say some more things about specific heat, right? So this is the relationship. This is the equation I showed you earlier. Q, the heat change, is equal to the mass times the specific heat times the change in temperature, right? And again, as we saw in the example I showed you before, we need to pay attention to the signs, especially how the question is worded. Because as stated here, if the change in temperature is positive, which is delta T, that means the temperature increases. That means that Q is positive, right? Which means that the system is absorbing or gaining heat, right? So if delta T is positive, now the specific heat and the mass are always positive. You cannot have a negative mass and you cannot have a negative specific heat, right? So that means that if delta T is positive, Q is positive. And that also means, obviously, that if delta T is negative, which means the temperature decreases, that means Q is negative, which means that the system is losing heat, all right? So we have to keep the units and the charges, not the charges, I'm sorry, the signs consistent when we're using equations such as the specific heat equation right there, all right? Now, there's another unit of heat or energy that is oftentimes used, especially I think they use it more in engineering, and that's the calorie unit. It's not a metric unit, but it is still used in, you know, professions like engineering and so on. And the relationship between the calorie unit and the joule unit is given right here. 4.184 joules is equal to 1 calorie. So we can express that as a conversion factor, and we can use that to convert from calories to joules or joules to calorie. And based on that conversion factor, then we can determine that water has a specific heat of 1 calorie per gram degree Celsius. In fact, the calorie unit was invented based on this fact here, this particular property displayed by water, right? And then now there's another unit of energy, which is known as the food calorie. And the difference between the food calorie and the calorie unit is that the food calorie is the symbol or the unit is expressed as cal with an uppercase C. So that is different from the cal with the lowercase c, which is used for calorie that we mentioned before. And 1 food calorie, which is CAL, uppercase C, is equal to 1,000 calories. So basically, 1 food calorie is equal to 1 kilocalorie. And that's a unit that is used in the profession of nutrition or nutritionist and so on, all right? Okay, so what we're looking at here, and let me just say this, the specific heat of a substance is a physical constant, just as how we have physical constants for other quantities such as density, melting point, boiling points, and therefore we can use it to help to identify the particular substance. So what you're looking at here is a short list of different substances, metals, nonmetals, compounds, etc., and their corresponding specific heat values, right? And as you can see here, metals, they tend to have relatively low specific heats, right? So aluminum is 0.902, copper is 0.385, iron is 0.449, and so on and so forth. So typically what you'll find is that metals have specific heats which would be lower than 1 joule per gram degree Celsius. And then you have substances like water and ethanol whose specific heats are higher. And in fact, among substances, water has among the highest specific heat value. In fact, I can't think of any substance right now that has a higher specific heat than water. And the reason why water has such a high specific heat is because water has a particular feature at the molecular level known as hydrogen bonding, which we'll get into later on in this course, all right? But simply put, hydrogen bonding is a relatively strong intermolecular force which requires a lot of energy to break, and that's why the specific heat of water is so high, because a high temperature is needed in order to free those water molecules from each other so that they can move around more rapidly, and therefore the temperature would increase as a result. So more energy is needed in order for the temperature of water to change by any value compared to other substances, all right? So as stated before, metals have low specific heats, and water, as I said before, has a higher specific heat than almost any other substance. All right, so we're going to stop here, and the next video we'll be dealing with some examples using the equation I just showed you, all right? Okay, until next time.